Hey, this is Coffee Compiler Club. We're here today to talk about compilers and maybe about bad keyboard interfaces on old Macs or on modern Zooms or something. There's been issues. Anyhow, we're all being recorded live. We'll show up on YouTube in a couple hours. I'm hoping today that we'll keep it a little more on track and a little more compiler related than last week. And for that one, I have at least one ready question, and that's, what about exceptions, which we lit into in Coffee Club just the moment we hung up from Coffee Club on Discord. We lit into exceptions. No one wants to say something about they're good, they're bad, they're ugly, checked, unchecked. Alan has something.
Okay, yeah. So, I don't know. So I posted this long thing about why exceptions are good, and like I didn't get any useful feedback besides that, like, oh, your writing sucks. So I don't know. And also that I had no facts to back up my opinions. So that was the other piece of feedback.
Yeah, I don't know. There was some facts there. I was looking
Say
for
no.
more.
Say no to exceptions. So
Just say no to exceptions.
I say yes to exceptions. That's what I say.
If you're gonna have exceptions, just do the delimited continuations thing. There's no need to only have to delimited continuations.
So I'm writing your pacemaker. Am I doing continuations for your pacemaker or not?
Don't have to it. If you're gonna do continuations in my pacemaker, don't just half continuation.
But you're okay with continuations in your pacemaker.
on this tangent,
yes.
Error code or type exception. So
we want a richer interface than a code. There are times when code is appropriate and it's fine. Generally, I'd like a richer interface than an error code.
What went wrong? 7.
Exactly. Well, then you look up no interpretable error code. I mean, whatever. You have to go reverse map it to some giant pile of no you screwed ups, and they're like, what the hell? E sector not found, and you're like, sector? What the hell? I don't know.
So the thing I wanted to say, so actually, exceptions are not implementable with continuations. So,
yeah, sorry, Shaw found the good error there. E-I-E-I-O. Old MacDonald had an exception. E-I-E-I-O.
Yeah. So there's this paper that Simon wrote, Simon Peyton-Jones, about asynchronous exceptions in Haskell. And so in particular, there's a couple examples of things that you can't do with continuations, because, like, for example, throwing an exception to another thread and interrupting it, you can't do that with continuations.
A lot of your continuations are single threaded, that's for sure. If your continuations aren't very good, I guess.
Well, wait. Very good means I've never heard of concurrent continuations. So this is always a single threaded concept for me.
Maybe we should start by defining what a continuation is.
Oh,
it's just the thing to do next. It's just the thing to do next.
And so it's just a function pointer. Just a function pointer.
Essentially, it's a function pointer with state. Yes, it's a closure function pointer.
In times past on single core machines, it would be your return stack.
So when you said function pointer with state, what you said is it's a trampoline potentially.
Yeah,
potentially it's a trampoline. Yes, that's an implementation detail, but yes, it's like a trampoline.
And how does that play out in the land of concurrent multiple threads? Because the normal assumption here is that I'm talking about some sort of mathematical definition of the program semantics, which is basically single threaded. There's no concurrency notion involved in that. So where does concurrency come into your function pointer with state?
Well, you basically call it on the other thread. That is how the continuation is run in this case.
Wait, Onat, just so you know, I saw that your mic was unmuted and it looked like you were trying to talk and we heard nothing.
Ooh.
Oh yeah, I was going to say like trampoline as in like saving some register state and restoring it later at a later point. Do you mean a trampoline like that? Because if we're talking function pointer and state, yes.
The goal is to simply send you from here to there and carry on over there.
Yeah, yeah.
All
Well,
right,
and,
so back to
and
concurrent
I
continuations.
used the term trampoline specifically to mean I have allocated a pointer. Well, I've allocated a block of something somewhere, and I got a pointer for it. And when I use that pointer as a function, my state gets restored. So yes, on a, that it could be registers or it could be whatever. I mean, it just usually it's just one value that gets passed to some other
Oh, yeah,
function. But yeah,
I have it also in my compiler as like I have like a safe place where I can restore to by like, okay, I just save all the registers including the stack pointer, and if anything goes wrong, like exception throws off, I can just save back to that, like I restore back to that state.
Okay, so you have some sort of event loop, like I hit Control C in my REPL, and it wiped everybody out and took me back to the top of the REPL, and I could go again.
There is no REPL per se. There is just the editor loop, and
Well, that's the REPL. That is your REPL.
Okay.
So you're reading in your editor whatever you're writing, and then you're evaluating it, and you're displaying it on the screen. And if you hit a magic button, you go back and reset that loop to the top of that loop.
There is no REPL per se because I recompiled everything from scratch.
No,
there is still.
Oh no, REPL can do that.
Yeah, that's a REPL still.
Oh, okay.
You read from your editor, you evaluate, that's compile everything, and then execute it all in one go. You're displaying the output of your execution. You don't like it, so you hit some magic button, and you're back to the editor loop, and you can go again.
That just to me, because what if you modified a file in your REPL? How are you going to undo it? Unless I misheard this.
All depends on what you're doing in your allowing or doing in your REPL. There's like the big REPL is I wiped my machine out with a format and I pulled it back from my backup.
There was a time, like there were times when I destroyed my own tools with my own tools. Like I made like a mistake where it's overwrite the binary, and I hadn't like maybe taken like a backup, and
I have totally done that.
Who hasn't destroyed his tools with his tools? Oh.
Yes, exactly.
Me, but I did give myself a virus with one of my programs.
Okay, good.
It was using IE6 embedded in Visual Basic and hitting a website that served ads, and it's IE6, so you get the idea.
I think I wouldn't say responsible, but I participated in the first virus that I had ever heard of, which was on an Apple II swapping floppies with the boot sector hack that would boot up, run a counter of how many times it had done things, rewrite onto the next floppy that got inserted with the counter incremented. And me and a friend at Texas A&M in my undergraduate days were trying to see how fast it would spread. And the answer was it overflowed the 1 byte counter we had available very quickly.
So Levo, you definitely had us at the combination of IE6 and Visual Basic.
Yeah, it's fun to learn languages sometimes and new things, but
fine.
Sometimes you don't know what's going to get you in trouble.
Okay, wait. Back to exceptions. What the hell, continuations? Okay, so Simon Peyton Jones says you can't do everything with continuations. Fine. When do I throw I guess I do throw a cross-thread exception. I want that thread over there to stop. What's the right way to get that? I've launched 1,000 threads across a cluster. Somebody's cluster clicked. I want to stop them all and try again. What do? Throw an exception, sit a bit, everyone's polling. What's the right way?
I wouldn't have done exceptions for that. That doesn't seem like an exception-y thing to do.
I eventually pulled a bit, but everyone had to pull the bit. Okay, fine.
Yeah.
So then why are you throwing exceptions cross thread?
Oh, so the reason you throw exceptions across thread is because exceptions have the right semantics. Because they act like interrupts. So like a normal value or whatever, like if you can't just stop a thread at like any random place, right? You have to find like a safe point or whatever to use the JVM.
You used to stop threads at any random place, and then we upped
Which sucked, by the way. Yeah.
Yeah, but we upped the game. Okay, fine.
And so the exceptions, it turns out that like they have this bubbling semantics. And so the bubbling semantics is exactly what you want, because you can say, oh, it started in a random place that I don't know, but then it bubbled. And so when I actually process the exception, I'm at like a catch handler or something.
You move it up some system of control to a place you can handle it, which means you understand the situation. Yeah, I implemented that fucking cross-thread exception throw in Hotspot, by the way. That rather sucked, but fine. It seemed unnecessary at the time, but it turned out to be a useful thing.
See, it's useful. Like I'm not making this stuff up.
No, the original one was thread death. The only way to stop a remote thread was to thread death it. But if you threw a random exception at any point in time, you wouldn't get your locks unlocked. And the JVM promised you stack-based unlocking. So if you took a lock, you had to unwind and unlock.
I'm also curious, in the conversation online, like the only thing that Levo and Matt have ever agreed on is exceptions are bad, which was kind of interesting. So, is it, I was really curious if that were more a reflection of the, how bad C++ exception implementations were early on, or if it's just that exceptions don't fit well outside of a GC language, which was the other possible explanation that someone offered.
The GC thing is kind of like a red herring. Like,
I can explain what my thought process was when I said it.
Hang on, Levo. Because you don't correct your program state if you just unwind ruthlessly. And so you're left with a broken state. Now, the GC finds the dead objects and cleans them up. But if I have a fancy hash table with fancy semantics and I take an exception in the middle of it and I don't preserve the hash table semantics, the entire hash table is now broken. But maybe subtly so. It takes a little while for it to crash and burn on me. And I have totally seen this happen before. So just the act of having an exception and unwinding stack frames and expecting the system to clean up after you isn't sensible. You have some other semantics you have to preserve all along the way.
Well, in theory, you have some kind of monitor. You're tearing down atomic units that can be torn down.
Well, it would be if I was doing like back-to-back transactions. And every transaction either committed or didn't commit. And then if I took an exception in the middle of trying to process a transaction, I simply didn't commit the transaction. And I always moved from a valid state to a valid state in some sort of nested valid state. I don't know what the hell it means. But if I take a random exception and you clean up the locks, which is fine, and you clean up the dead memory, which is fine, and you leave everything else like half schmooed, you're still busted.
It should be like a custom restart for a custom system. If this is a thing that the system cares about, like the language can do only so much to anticipate what how the state could be restored. Like,
so in the land of OSs, the big Control-C kill -9 brings you back to the shell script state, which is a reasonable cleanup. It clearly leaves file state messed up, but it cleans up your processor memory state. So there's at least a partial cleanup going on.
So what was Levo's explanation for the his point of view on this?
Well, actually, I just realized the easiest way to say it is it's a lot easier to mess up C++ code or C code than it is to mess up a GC language.
Maybe.
But is that why you don't like exceptions? So what's the
my reason is because if I'm writing Java, C#, whatever, usually I just want the code to work. If I'm writing C++, I want it to work well, or it might be complicated, or I want it to be fast. Exceptions, it just makes, if every line could just like throw, it's so much harder to understand the code. And if you're trying to make it work really well, like well enough that you're willing to use C++, you really want to understand what lines are going to be doing. And just
It kind of
jumping
sounds like
3 functions away is going to be really confusing.
What I
it
heard
sounds like
was, sorry, Shaw. What I heard was exceptions are good for languages where you don't care so much about the quality of effort or the, how you handle things and the robustness. And
It's
if you
more
need a
like
robust answer, you don't do exceptions. Which actually sounds pretty familiar. I've heard
I
that.
accidentally clicked on me twice. It's more like if you're willing to put up with C++, something has to be really complicated, and you don't want really complicated exceptions together.
I would also add that this is independent of C++. Rust doesn't have exceptions. It uses the result type, and people have been using Rust for a while now, and really everyone is fine. So I think that what is missing is the actual use case. Why do we need exceptions if we already have result type in Rust?
So I think it's more of a style opinion than that. The advantage of exceptions is I can take a whole bunch of places where the same thing could be thrown and handle it in one place. So now you can see the core logic that's going on without getting distracted by a whole bunch of irrelevant error handling logic.
Well,
the disadvantage of exception is the exact same thing of there's a bunch of error handling logic that I can't see explicitly because it's somewhere other than right in this moment where it can be thrown. So the advantage of doing everything with result types is that it is more explicit. And the advantage of doing things with exceptions is it enables you to pull out exception handling logic into a place where it's not right in front of you. And that is a very stylistic choice of which kinds of exceptions need to be visible that are being handled and which ones don't. I really don't want to handle the what if I run out of memory every time I do a function call.
I agree with the stylistic choice, and I actually think that's where the language designers can meet people both in the middle. For example, in Rust, error handling logic is just often adding a question mark. So you don't have to write something like in less designed languages, say Go, when you have an if statement around every single error, because that would be insane. But in every designed programming language, you can usually have a dedicated syntax for that, which alleviates the error. So question mark in Rust, or for effects in Haskell, you have a do notation where you just write ordinary code line after line after line after line. And you do have a propagation of actions that happen under the monad out of that. So I think it's to a large extent it's just about syntax, but semantically, you may be able to get away with an error type like in Rust.
So I'd like to hear what Shaw was going to say earlier.
Yeah.
I was gonna say that the reason why C++ shouldn't have exceptions is because you don't want exceptions in C++. That's what I was gonna say. Is the reason why it shouldn't have it is because people don't want it in C++. And I think there is both design space for languages with exceptions and for languages without exceptions, and that you can make a valid case for both.
Can I ask a clarifying question?
Yes.
Would you still want long jump to be available?
I never use long jump. I prefer exceptions to long jump.
And you kids and your freaking exceptions.
I don't use either. For instance, I write C without what is it, like something jump set jump dot. It's a weird
set jump
name,
and long jump, yeah.
Yeah, set like the I've just never touched set jump.h or any of its functions. I just don't do that. I do the Rust thing, but like not. I just return a struct that has a Boolean in it, and or a pointer that's.
I like the way you said. I like the way you said the earlier thing though, because I think it does really reflect what Levo was saying, which is people who use C++, they don't want that freaking baggage. They've chosen to enter the elevator of death, right? And they're taking the fucking elevator of death to wherever it goes, whatever level of hell, and they want the full. They want the full ride. They want the full experience. So exceptions cheating.
Yeah.
So just so you know, every time you launch a JVM, the initial thread does a bunch of setup, whatever, and then he wants to become a normal Java thread, which wants to be on a 2 mega line boundary. So he set jump long jumps himself to a pre-allocated stack and lives the rest of his days on that stack. All other threads I get out of P threads, they also don't start on a 2 mega line stack boundary. So they all take a set jump before they begin life. So it's not, they never return. They do I hammer the bits in and I say long jump and you are never coming back.
Well, like, long jump makes sense if you're never coming back, but like for a form of control flow, I don't like it.
Okay, fine.
Like if you're trying to align your stack, that's kind of the only case I would ever use it. And I don't have that requirement in any of my programs, so I've just never touched it.
We used to have a lot more.
I understand the concept.
Sorry, we used to have a lot more of them in Hotspot, and we eventually got rid of them all for the safe point only happens at certain places where now we can do a structured control flow in a sensible way when you throw exceptions and stuff like that.
One of the things you can note is that you can implement exceptions using results, just like compiler in, like, hey, statically analyzed, I throw an exception somewhere in my deep stack and just result out like automatically. And you can implement, like, they're exactly the same in that one can implement the other and the other can implement one.
Sorry, say again, what was the
So you can implement exceptions by just having every function return a result. And it might not be fast, but you can then optimize it away if you never return the result.
So you're saying, for example, if you generated C code from an arbitrary language, yes, of course.
Yes. Like this is how Python, not Python does it, but Python's written in C, and it doesn't use long jump internally for its exceptions. It uses some other mechanism, just its own stack unwinding. And it turns out that like exceptions are good if you write in a style that requires exceptions, and they're bad in every other case. That's just my take. Like if you want exceptions and are used to them, they're good. If you use it once in your 10 million line program, they're maybe bad, you know? Like if the new guy's like, yeah, let's
sane cleanup plan. Most exception handling code I've ever seen was basically never tested and was broken and would throw an exception itself if it were actually ever executed. So it was just never helpful.
We should probably come back to Matt because, you know, he had the point that, you know, some languages, you know, ones that afforded a design, so not Go, you know, like you can add a question mark to say, you know, this thing could have an error in it. Or in Java or C# or Python, you just add nothing to a function call and it says something can go wrong in there. So I'm curious what Matt's point of view is now that he's heard Levo's and Shaw's explanations.
Don't forget call stacks from hell. Like the exception call stacks that I've seen were like not pretty. I mean, C++ is indeed like a language from hell that.
Okay, I want to hear Matt's answer though.
One of my issues is I posted a link which shows the problem is the impact on code complexity. Is that you try and have 5 lines of code when you check for a field or data member of one object, you check for a data member of another object. Conditionally, you say something about them, and then maybe you print one message after that. So 5 lines of code, ordinary code we write all the time. So how many code paths you can have with those 5 lines of code if you have exceptions?
Oh,
so you have. No, you have three non-exceptional code paths, right? You have something that happens before, you have something that happens conditionally in an if statement, and you have something at the end. Guess how many you have when you have exceptions? 20 more. And that's not really C or C++ issue. I mean, this is an issue of having every single operation being able to throw. Yeah. And this throw may or may not happen. It may or may not cancel the subsequent operation depending on what is the exception handling. I think there is a design space for exceptions here to make them ergonomic. As a possible counterpoint to myself, I can add that I am watching with what Swift is doing with typed throws. Yeah, it looks to be the first attempt to design exceptions with types, and I do not count Java as that. I think Java was completely not the approach to even attempt to have typed exceptions. It's a bit like Go and error handling. There was a syntax for this, but there was no design. So Swift has been doing pitches for several years now. There is one that just started yesterday, so I will be watching this with interest. I think there has been a lot of thought put in that design, in that it does use type inference and existential type, so you don't have to type the annotations in every single place of your code. It is actually using contemporary programming language features to buy you some ergonomicity. So I will be interested how it's gonna be realized.
I designed error handling in my language. I can explain that if you guys want.
This is you're returning error codes or something?
Yeah, so instead of exceptions, which I really think is really bad idea for native languages, what I do is I have a standard set of enums. I just call it an error enum. You get like a bad parameter, invalid, or just whatever. And I plan to implement error types, but that's not done yet. So essentially, you can use a bang or exclamation mark to say if something is an error type. So you could have int bang or class bang, whatever. So the idea is,
can you
if
got any code to show?
Yeah, I think I do, but
yeah, but
give
int
me a minute
bang.
to look
So
it
just
up.
translate his int bang to a union of error code or int.
Or an int.
Yeah.
Just give me a second. I think I do have some code I can just like link.
Well, I can give you the screen too here.
Sure, yeah.
Okay,
take the
why don't you
screen.
talk it out because you don't have it ready, and then just ask you.
No, it's up now. I'm just gonna look for the share screen button. Entire screen. All right. So, so you can see the int bang right here.
Can you put a heavier weight font, larger? That helped much.
This?
Oh, there's the bang. Now I can see the bang. And that means that you can return any arbitrary integer or an invalid parameter, which means you have two returns. I take it. I'm asking.
Yeah. So I'm kind of hacking my way around my language. So most of the time, I feel like if you're using an int and it can be an error, the int is almost always positive. So I have a thing where you could do int or error, like a pipe.
It's like
mean it's a union.
Like SIG's error codes.
Yeah. Let me just. I guess I just outed what I'm working on right now, but
you're so doomed.
Yeah. So if you write this function, no, some. See, I'm not sure what you guys are seeing because I have a thing blocking my screen.
You got not a whole lot left for code in there, but it's easy to read.
So in this case, this will be a union. I'll just call it a tagged union. So this would be like 64 bytes. It's either going to be an int or an error, and you have another field to say which of the two it is.
So you return two values or two registers or something. Yeah.
But for now, what I'm planning is if you write it like this, it's just going to be positive values only or an error enum. But I'm not 100% sure if I'm going to keep that because I'm pretty sure a lot of people are just going to be annoyed that they have to write out this instead of this.
But you're returning But you're returning an error.
How are you indicating positive values?
Yeah, I would say call it a uint, not an int, because you can't have any negative.
No. It's basically a 63-bit int. So if it's negative, that's it's the error enum. If it's 0 or higher, it's going to be a 63-bit int.
Oh, so it's unsigned, right? I would put uint too. Yeah.
Yeah, I'm saying declare it unsigned because you have to return either an unsigned or an error. I cannot return negative 17.
It's a uint63 union with an error code.
Yes.
People will think that if it's unsigned, they're going to have 64 bits of unsigned, which is not.
I would claim. Well, fine. There's uint63 as well, but I would claim that you could make that clear in the language. It's the same as JavaScript says. You get 57 bits of an integer. Fine. It's big enough that only very special cases blow it out. People doing hash codes with longs or randoms.
You can also do your enums based on min value +1 instead of 0 -1, etc.
And Shaw, you can put that in the doc. Shaw has a more complicated suggestion. Leo was trying to write something very short to say I have an error, and therefore I'm also only returning one value. And if you're doing cogen, Levo, all the registers are available for efficient returns. You could totally return 2 registers, a 64-bit int and another register.
Yeah. I'm still thinking if I should just not do this hack where it's only 63 bits.
The calling convention of most systems will allow you to return a 64-bit integer and another 64-bit integer all in registers, and it won't be any slower than doing like the aliasing that you're talking about.
Right. Yeah, it'll be just as efficient. Yep.
If not,
I guess I should.
Dependency, but
yeah, I think I should just allow the full 64 bits, but right now it's currently implemented like 63 bits. But anyway, the idea is if I want an error, I mean, if I call a function and it has an error, I want to either, well, okay, in this case, I want to explicitly handle it like right then and there. So like Matt was saying that in if statements, the conditional can throw, the body can throw, and there's like 20 different places where it can throw. So in this case, only the function can have an error, and you have an error block right after. When you do this error block, like you can see that this is either going to be an int or an error. But since this error block exists, A is always going to be an int. So there's less, you don't have to check if it's an error.
I
so
like this explicit method,
and
I like that you can guarantee that the result is always going to be an int. And actually, to me, that's the point of exceptions are being a little bit like implicitly nullable types. You have languages that you can write a function that says that it returns an int, but it doesn't return an int because it can return a null. And then when you try to access that int, you won't get a value that is an integer, but you will get null pointer exception. To me, that's a bad design. And similarly, a function that tells you that it returns an int, but actually it doesn't, but it throws an exception instead, is again that function that violates, I would say, what is a good design principle of type systems, is that the types are what they say they are. So this is my issue with the current ergonomicity of the exceptions from the user of the language point of view, is that they're a bit like implicitly nullable types. Everything can be null, even if you are trying to say you definitely do not have a null and this is actually an integer. And you have no way of saying in languages with most languages with current exception that this will not throw. And actually integer is an integer. I would like a language where integers are integers.
So let's be a little clear here about what it means to not throw. Because in most languages, you don't check for stack overflow, but stacks are finite sized. And a function call is going to burn some stack space. And short of doing some sort of real finite, hardcore counting of things, that can throw a stack overflow. You can throw stack overflow. You can throw out of memory. Reasonably commonly, you can throw range check exceptions for out of bounds. The C will never throw range check exception, just die. But otherwise, you can throw. And these exceptions are things that I'd love to catch in my debugger and fix them, find them. That's useful. But I don't know what I would do for recovery on that thread. I mean, just in general, like what is the normal recovery? I got an out of memory.
Yeah, I agree. I think that's also not the use case for exceptions, because if anything, exceptions are a use case for recoverable errors. Okay, and here we would rather have a debugging information point.
What I heard you said was there are certain classes of exceptions which shouldn't be exceptions. There just should be panics.
Yes, or dump debugger information, or prepare for restart application.
That's not a composable design. So it's just, for me, it's a non-starter to begin with.
How do you recover from Stack Overflow error?
I can go through my example.
What do you mean you? When you say, how do you recover? The computer doesn't die. The operating system doesn't die. Somebody fucking recovers from it, right? Yeah. Why? Because it's composable. If you do what you're describing, it becomes non-composable. So you can't build an operating system.
But wait. I said it may be a recovery point. What I'm saying is that it doesn't have to be exception with full generality of exceptions. So I'm asking if you are insisting that no, it has to be exception and nothing else, what's special about exceptions that make Stack Overflow errors more recoverable than any other recovery mechanism you can program.
I think you already explained it when you said a function returns an int. You want it to only return an int. So that means that nothing bad can happen in it because that's not reflected in the type int. I think.
Well, no, but the program can be interrupted. But that's a completely different thing, and I would not count them in
the 1970s. This isn't the 1970s. There's no such thing as a fucking program.
Cameron. Data center is a computer, and a huge distributed application running on the cloud is a program. Okay, so we can set that straight. So yes, even today we have programs running on computers, even if they are cloud services running on the cloud in data center. It's still the same terminology. And that system, distributed system, has to be able to recover. And I claim that exceptions do not help you in this distributed system recovery in any way, shape, or form. So I think I don't really see the argument what is special here about exceptions compared to any other recovery mechanism you already have to implement yourself in a distributed system.
So I implemented a distributed recovery system in a distributed cluster that started with whatever exceptions, but the base language would throw exceptions at me for whatever reason it did. And I did make it cluster friendly, but maybe I wrote it myself. I didn't get a cluster wide exception recovery out of the language.
Yeah, and that's kind of my point, that if you really want this as a serious recovery mechanism you're gonna use in productions, I think exceptions are the 1980s approach when we had one computer disconnected from the network with a finite set of errors that programmers could look up in the manual and be prepared for. But I think it's a very vastly different design from the world we inhabit today. I just really don't see the connection of recovery mechanisms you implement today with exceptions as we have with most languages.
So what would you suggest to be the recovery mechanism when Stack Overflow or out of memory happens?
I don't think there is a one general recovery mechanism. And yes, that's bad news. And yes, you are going to have to think about this when you design your system. Unfortunately, I don't think today's languages provide you one single recovery mechanism that can always work.
All right, let me. This is a very interesting conversation. We should keep going, but I want to see if Levo's got something he's been writing away, and I want to see if what do you want to say there, Levo? You're making something.
Yeah, there's much more to this, so I figure I should go through all of it. But do you guys want to hear more about this?
Well, this is like grist for the mill on what to do with exceptions. Like Matt just said, there is no one such answer. Provide several. I'm not clear that that's a good summary of Matt's position.
It's only going to take me like 2 more minutes.
All right, go.
Yeah. So one of the things I wanted to do was look up like the index with the function, and I noticed that one of the times I wanted to do it, it could return an error. So I just kind of got annoyed, and I said, okay, I do got to implement a try. So if this function has a compatible error, so if your current function is an error type and your function you're calling is an error enum, they're not exactly compatible, or maybe the other way around makes more sense, but they're not exactly compatible.
So what is your talking about with the question mark? Your exclamation mark is the question mark Matt was referring to.
Yes.
I
think the question mark was the one on the try. But what is the semantic?
The question mark replaces the try. He would simply, in the language Matt was referring to, it would be FN open paren 1 2 3 close paren question mark, which means I'm calling this thing and it may fucking return. It may cause me to return from this point with an error.
Having try be prefix seems like a bit of an issue, because if you want to call the result of function, but function might return an error, you have to wrap it in parentheses, and that's like the async await problem in JavaScript, where it's async is a keyword that operates on something postfix, but it's a prefix operator. I don't know. That's just my take.
I had a different question here. What is the intended semantics if I put a try there or a question mark? I can throw out from that point. Is that what I heard Cameron say? There's no attempt to do the assignment to some array, but there's no attempt to go to the next statement either. A same as B. Yeah, right. But in both those cases, you don't. you don't get to run the sum array assignment. You always throw out of the current function we're staring at. The whole screen function we're staring at gets thrown out.
Yeah.
Okay.
So
hard.
What if you want to
figure-
break out of a while loop for it?
Well, then you put a try catcher on the while loop and it breaks out, and there you are.
Well, try only works on the it has to be right before the function call. So
Yeah,
error
yeah,
is right after, try is right before.
Okay, right. And there's some question mark comment that says, or a bang or some other syntax that says there's another way to say try. But in all these cases,
in my
have a-
language, you only use the bang and question mark to say if it's an error type or a nullable type. So you never have the bang here unless it's like this kind of bang. But as in a not. But anyway, one of the other things I really want to implement that it's not done, and Zig beat me to it, is error defer. So print so if this triggers or an error block triggers, because it's an error type, it knows that it should execute the error defer code.
That's the finally clause of in a try finally.
You can think about it like that, but it's just it makes everything easy. Pardon?
Do you have just plain always defer, like not like defer if there's an error, but like always defer, like at the end of our block we want. Well,
See,
okay.
I implemented both of these in my prototype and completely forgot to do it in my compiler.
If you plan to do both of these, why don't you have a success defer or like an everything's okay defer? Because these two create like a void where there's like, well, we can defer always or defer if there's an error. And if
I was thinking about that, I couldn't think
of
a good word, and I know that D uses success. I think it
yeah,
uses
like
success.
I have gotten this idiom from D because it is one of the languages I think has like a good like okay defer, maybe. I don't know. Like I always have a problem with languages with only error defer, because it leaves like, then how do you do something if there's only success? How do you like do a network request if the function succeeded? Well, you could take it out of the function.
I agree.
You set booleans everywhere and test them. Yeah, that's a little
yes.
Yeah. So
it feels like a map.
Here's the thing that I liked about C++ for doing the defer, which was I wrote a one-line bogus constructor variable at the start of my function, and the destructor on that variable stack destructed on all exit paths. That one I used the hell out of and really loved. It meant that I had a defer logic that I didn't glump all the different defer things I wanted to do in one spot. I just put a ordered list of things that did a setup, and then I got the unset in the reverse order on the way out under all conditions. And then, just quit sharing.
Basically, RAII for all practical purposes, minus the resources.
Yeah,
so just AII.
It was very, very convenient to deal with setup and teardown, including we did blocks and I don't know, all kinds of connections to this and unconnect when you're done, and put a temp finger into something that had to be there for concurrency reasons, and then pull it out when you were done, stuff like that.
But I think
save it, Levo. We'll come around to build systems.
To be unfair to Levo, I think the problem is that there is one part of what Matt's saying that I agree with, which is, let me restate it differently, Matt. I don't mind people throwing. I generally mind people catching.
Yeah.
Like that. The problem isn't the throw. The problem is the thought that people can recover, right? So generally speaking, and this is kind of the flip side of what I've tried to say before, that exceptions should be exceptional, right? Like if you're writing code to catch exceptions, you're either building an operating system or you're doing something wrong. That's I can't really.
So you want to stack trace and abort?
No.
No, I want to use exceptions as a panic because they're exceptional. They are panics. Okay, you want to call them, you want to rename them panics that you can catch? Sure, call them panics you can catch.
The OS certainly catches panics.
And maybe that's Matt's point.
I thought you were trying to say you should never catch an exception.
No, it's like most of the people who
You
catch
should never catch it.
they have no way to recover. So if you had a way to recover, I don't care. It seems reasonable. You should catch and recover. That's great. Most people who catch log and rethrow as the best effort. And
Right.
and they, if they didn't do anything, you would get a log and rethrow. You get a log at the top anyhow. So the
Also,
log and rethrow was always a waste of time.
So my problem is the implicit alteration of the control flow and the permutation of the code paths that result in every single function you write due to this implicit alteration of the control flow. It does contaminate the type system. Again, you cannot really write a function where an int is an int. If you have a panic that crashes, then that's fine, because then you still rely on the invariant that as long as the program hasn't crashed, a result that you have obtained from a function that completed is an integer. However, if you have implicit cancellation, which may or may not be handled, which is what exceptions are, then you do not have guarantee and you cannot rely on this invariant anymore. So panics, at least to me, I don't think panics are a one universal solution, but I don't think that's what anyone is saying anyway. But at least panics have this one advantage that you preserve this invariant of the type system guarantee.
So I think there's a different thing here. If that function throws an exception to in, then it comes back on a different path. The return path, it has multiple paths out. One of them is the normal flow where you get an int. The other one is you took the exception path. You're in a different spot. You expect an exception, not an int, and you totally know what's going on. That's the the catch clause. So I think it's not fair to say that it sort of messes up the type system. It's clear that the functions have two exit paths.
Well, the problem is that this is true for every single expression that calls a function. That I would refer again to this example by Herb Sutter, when you can have very benign looking code, when you just have object access Y data member, object access another data member, with the data member being a property, which is a member function or a method. And again, if every single method can throw, then of course you no longer have this guarantee of the result type of a method, even if it's just a part of a expression as a sub-expression.
No.
The problem
that's a function call.
The problem is to me at least, the alternative is equally hard, because if you really want to guarantee an integer, that's not always the case. So the type system, either you are in one for the static analysis, the type system should guarantee that cannot be anything other than int, cannot overflow and be pure. It doesn't have side effects, but that's
runtime checking. Yeah, runtime checks for overflow are totally fine. That gives you invariant that an int is an int.
Okay, that's fine. Question that leaves the question what to do if the check fails, what to do. Yeah. So exceptions are panic.
I mean, you can no longer guarantee maybe that integer is gonna access customer's bank account. You definitely don't want to continue in every case.
Of course. So exceptions.
You just renamed exception to panic, though. That's cheating.
But panic terminates, whereas exception propagates and continues with implicit control flow. So it's a very different solution.
Define terminate.
Exactly. Define terminate.
I think I need to
blow up.
Right.
I think I need a definition for exception we are using here then. If there is a definition the
trick. I guess what I'm saying is we're probably not disagreeing. It's just we're using different words.
It may be violent. We may be in a violent agreement. Yes.
The trick
like just catch fire. No catching fire, please.
Is that exceptions make the function a way to make, let's say it's total, because you have something to return when you don't have something to return.
But your computer didn't catch fire and burn to the ground, so you got back to the computer somehow, which meant the OS didn't panic. The OS caught your process, and you got back into the, if I wanted to make a match term of a large scale program system, if you threw a panic, I would watchdog timer would re-kick the thing up again, and that's the recovery.
So that's the beginning of, at least me, the split between the error and exceptions. So an error is something that you return when you don't have the expected input, and exception is something that happens exceptionally. One in 1 million times maybe. So it's not something that
you can just recover out. outside of the OS? There's always a recovery. That's one of Cameron's points here. There's always a recovery.
Okay.
Okay,
Yeah,
so now
one note from me though, I would really, and I had to learn this myself, but I would really avoid of thinking exceptions are something that happens exceptionally, because this is a circular definition, and it's better to break down what exactly do you mean as exceptionally for your system.
So
I
exception
had to
is
learn this myself, but it's a trap.
so
That's
let's say
why-
okay. Stop. Let's say you have you're driving in a car. An exception may be something that you can allow you to drive for a little more, but you are already alert that your car is no longer no longer running as usual, as normally. So a panic is that you are about to crash in the very next second. So that's at least to me, I can interpret an error. That's something that the car can really it becomes really dangerous to
I think I would say
go,
then
but exception.
unrecoverable error. So then you are talking about unrecoverable error.
So
right?
it's not okay. That's the exception. At least I will interpret it that. But an error is something that it's bad, but it's not really bad. So it's about to get really bad, but it's not bad right now.
So there's a level of where you expect recovery to occur from.
So what is the check signal in the car? Is it exception? Is it an error?
Yeah,
Is
Levo,
it
that's not even the case. So don't go there because.
So it's an indication that something is wrong. It's something is wrong. So you should do something about it. So
but it's not, right away. Well,
Yeah.
the limitation of the car analogy is the time on it, but it makes some sense. There's like,
that's
I
what
had no
thought.
idea you guys were so passionate about exceptions.
oh yeah,
So
oh yeah, and seg faults, hotspot throws and catches seg faults all the time. Just letting you know, they're part of your.
I was trying to make
normal-
a joke, but I didn't know how it could come off.
Part of your normal everyday Java execution is to throw and catch seg faults. Fine. Where was I going here? Yeah, there's like a levels thing here. There's like, what's the recovery expected? And one of them is the programmer inside the process, and one of them is the OS is going to catch you, and one of them is the Ariane 5 rocket's going to crash, and the recovery is there's a big, hole in the ground and there's no moonshot.
and to mention where you're about to catch, you can do something before you crash. So you can do something at the last minute. So
yeah,
that's-
someone's going to recover.
I think the other thing to keep in mind is that an exception does not communicate with the caller. And I know that sounds really weird, but you're not communicating with the caller. You're communicating with someone who's somewhere in the call chain
Yeah.
Mhm. Yeah.
that is expecting something to go wrong, right?
Yeah.
So, but the caller could not expect it, so it doesn't.
The problem
Matt's
with it,
problem is fundamentally that C++ and Java and so on made exceptions so freaking simple that people use them as return values because the same languages made return values impossible unless you only want one.
Multi-returns would be nice.
yeah. So
No, there were other calls for exceptions that
when
I saw. This
when you
debate
write
is old as time.
when you write code that can abort at any time, so if you don't check the code before you has thrown something, it's like I'm hopeful that nothing will go wrong. So it's kind of ignoring the fact.
Or to be fair, you are fine with propagation up the call chain, to be fair.
Okay.
You are still communicating with the handler, and the handler may not be you.
Yes, yeah. So it's an unwind up to the point that explicitly said, I want a chance to handle it.
I want my unwinds to have a ruler. They wrap your knuckles if you log while you're unwinding. Just the number one.
We beat exceptions to death. It's a
Yes,
55.
here's 1 million gigabytes of useless stack unwind info, and somebody handled it anyhow. But why did we have to spew log for JDeath? Fine.
So I
Finally.
want to go back to Matt and ask him like, so he was saying he didn't like handling Stack Overflow with exceptions, and so he was saying, you know, so there's many mechanisms for handling it, and so the question is like, what is the interface in the language for handling Stack Overflow, right? Like with exceptions, it's very obvious. It's like, oh, well, I have a Stack Overflow, it raises an exception, and then I use.
By the way, it's not nearly as obvious as you think, but let's hear Matt's answer. But I can tell you the shit that goes on a Stack Overflow. It's not as obvious as it looks.
So,
Matt, are you up to?
Well, maybe less.
Yeah, I think there's one simple answer actually. I mean, one design that I have seen is basically a configuration for asserts, because one thing I would consider is to treat it as a configurable assert, when configurability is what the assert violation handler is supposed to do. And that is something you see in languages with contracts, when there's design by contract spiel, when you can configure what's going to happen if the contract cannot be satisfied. You need to have a contract violation handler in general, whether it's a stack overflow or whether it's addition that overflows, because the function that relied on that contract, it cannot fulfill its post condition because the precondition failed. And similarly here, if you're calling a function, you expected a result from that function, but that function cannot produce that result because it had to stop due to stack overflow. So that function you are calling, it cannot satisfy its post condition, so it cannot give you your precondition. So at that point, the condition already failed. So you may need to have a mechanism to configure the violation handlers. Some Erlang systems allow you to configure that. There's also the proposal for the contracts with the contract violation handlers, where I stole the name from.
So I want to say, I'm looking at the definition on Wikipedia right now, and it says that the definition of an exception is that if a procedure has a precondition that it cannot satisfy, then it raises an exception. So
in C++, it's called contract violation handlers, and you use this with exceptions disabled. So it's an orthogonal mechanism, at least in the existing language.
And you do it with more stack space hidden away somewhere because you didn't have any when you started.
Oh yeah, and you also need this for exceptions, by the way. Exception mechanism, at least in C++, you do need to have separate pre-allocations for exceptions in C++. Because again, as you said, you may not be able to allocate otherwise when the exception happens.
Yeah. So I'm gonna tell you what the Java exception semantics are for Stack Overflow, unless people just don't want to hear it because they're entertainingly confusing. So there's some point somebody threw a Stack Overflow because they touched some piece of stack that was too far past. And then we run forward to a safe point. We guarantee that there'll be enough stack available for that by having guard pages. And when you hit that safe point, we slow Stack Overflow and we unwind a frame until we get a catch for Stack Overflow, which you can totally catch. And at that point, if you have not unwound enough, the semantics are you throw again immediately. And so you can have a recursive stack of Stack Overflow handlers up to you run out of stack. And this is the JCK test, do this stupid thing. And they're running a counter as they go up, they go. And when they get a positive counter when they go in one more depth, and they get a negative counter when they throw and catch. And the counters are all running in registers after optimization and not in the interpreter, because the semantics didn't change for the interpreter or not. It's very interesting. But you just throw until you unwind the stack such that you can now run the Stack Overflow handler without actually needing any stack, without needing more stack that you have. So some number of Stack Overflows, some number of call ups will happen. Some number of Stack Overflow exceptions will get virtually thrown, unwinding as you go. And it's not necessarily the first one that you get to do any actions on. It may be that you have to unwind 10 or 100 handlers before you can actually have your handler say, call system.error.println.
What I think is interesting here, Maurice, there's an unavoidable bit of horrifying thought you always have to write one way or another. And I mean, the choices here as to how to make it ergonomic from the user.
Yes.
I think one area that is underexploited is what it's only starting to be a little bit picked on now is the effect systems. Because we are talking about effects to an extent, and exceptions can be effects. Modeling those effects in the type systems, I don't think that has been explored in mainstream programming languages as much. But there are some research languages like Coca, for example, that are trying to.
You got a link
I will
for
throw
that?
it. Yeah, just a moment.
More exceptions, yes, more exceptions. I'm looking at the comments now.
I guess that's the question. Is like, I mean, so like clearly, languages will have their own implementation of exceptions, and that may or may not have things like fancy Stack Overflow handling. The question is like, what is the definition of an exception? I mean, are you saying that like?
That's a good question, actually, because I think we have started with different definitions. For example, for me, that was mostly unrecoverable error, but I have learned that error can also mean different things to different people. So I think an excellent question, and I agree with Alan. That's the question to ask. Maybe we should have started with that.
An exception is input for which a function cannot give its output. So
exception is not an input.
That sounds like contract violation. Because
okay.
that is we cannot fulfill a post condition, right? That sounds exactly like contract violation.
Yes, Lebo.
But I don't think that all contract violations should be exceptions in the sense that exceptions are implemented in mainstream programming languages today. And I had to be this one because I had to be precise what I mean.
Exceptions
For example,
means
we don't need always to have stack unwinding feature for every single possible contract violation. It really is okay to crash the program, and maybe you have a higher level system that will restart, because one issue that we kind of didn't cover is that recoverability also has different scope. By what I mean is that what may be locally unrecoverable for a given component may still be totally recoverable for this overall system under which this component is a part of.
Right, that's what I meant by composable. It has to be composable.
Well,
right, so I think we are in the violent agreement, and that's it's only my belief is right now that exceptions may not be the greatest mechanism ever for that, and effect handlers look more promising on a system design level, but this is an evolving area, to be honest.
Matt earlier said exceptions are not exceptional, and that's why I have error handling and I don't have exceptions, because I want to handle errors. I don't want to deal with exceptions.
Yeah, and I would not use exceptional, because it always leads to circular definition. I think it's always better to break down the exact characteristics by what you mean by exceptional in your particular circumstances, and this will differ. And that's why people argue about exceptions, because for everyone else really has something different in mind when they say exceptional. A web developer has a very different thing in mind than an automotive car designer, for example.
I'm still surprised that Zig was the first language to implement error defer.
No. Things very similar to error defer have been around for a long time.
I don't know what languages or what
so GNU extension for C has this ability to handle things as you leave the scope. Yeah. I always forget what it's called.
Destructors in C++.
In C, no, I'm talking about C, pure C. Well, not pure, because with GNU extension. What's that called again?
Oh God, no, I don't know the GNU extension for this. I think I've heard about it. It's not optional.
Oh right, D did have it, but it's tied to exceptions, not error values. But yeah, the D did actually have it. It's too bad that D never caught on. Every time I look at language, it looks pretty good.
Somebody said something about why it didn't catch on. I don't remember.
Well, GC
I just assume it's because
nobody liked it.
I just assume it's because if you're garbage collected, you can't beat Java. So, and they went garbage collection.
No, I can give you the Reddit comments about why D didn't become successful.
What's that, Yorick? You're on mute.
Hello?
Yeah.
There we go. I had the volume low. No, I think as I wrote a little article, I mentioned there that I tried D and that I bailed out. This was in 2015. At the time, the problem I think was that D version 2 had fairly recently been released. I think in like, let's say a year or two before that. And so there were quite a few people still on D version 1. And then I think D version 1, they had actually 2 competing standard libraries. I might be mixing up with D1 and 2, but either way, there was this sort of split similar to Python 2 versus Python 3, where a bunch of people were like on one flavor of D and a bunch of others. And it seemed at the time that the sort of newer version they were supposed to be using wasn't really used that much. So there were very few libraries, very few users. All resources were basically pointing to like these conflicting versions of D. So you really have to pay attention. Like, okay, I want to learn D. I have to make sure I'm actually learning the right version of it. And I think the second thing there is that I feel it's kind of the case where it's too similar to existing languages for people to really give it a shot, right? As an example, if you basically take Java as a language and you change the syntax a little, for example, people might be like, oh yeah, this looks nicer, but why bother, right? That's such a small difference. It doesn't really justify the cost of having to switch my entire stack, my entire team, etc. And I feel that probably the problem was a bit that D in that sense is a bit too similar to Java, in the sense that it was kind of like a C++ like language, but with a garbage collector, easier to use. It did have C++ interop, but I remember even that being fairly limited. So I suspect that probably played a role in that. Now it has gotten a bit more popular since. I believe Facebook at some point used it for a while, so it gained some sort of popularity because of that. But I think it has sort of faded again. It's kind of hard to sort of figure out. So I think that's basically why, like, it wasn't. It's an incremental improvement, which is nice if you're starting new. But if you already have this established thing, then you want more than just an incremental improvement.
Yeah. All right. What else? Have any other raging?
I have actually a topic, but might be because it's a bit of a big topic, which is thread scheduling. So the context there is somebody made this. They have this sort of benchmark repository, and I think they rank some data and get the top 5 or something. I didn't fully understand it, and like most benchmarks, you look at 10 different versions, they actually kind of all do different things. So it's not the best benchmark, but whatever. They added a implementation for Inco. I looked at it, cleaned it up a bit. Most notably, it took 6 seconds, which was 6 times slower than Python, which was a little, I was a bit like, I knew it was slow because I don't apply any optimizations. But give me a break. This is, stupid. Well, what's going on? And, I cleaned it up. It helped a tiny bit, but not much. And then according to the profiler, it basically said 40% of your time is being spent in the fuel checking mechanism, which is used to determine, like, hey, should this task continue running or should it yield? The mechanism for that is very stupid. There's a flag stored in the a number stored in the task, and it is reduced. And once it reaches 0, it will yield. And that check is currently performed after every function call. So it is like, I knew there was a cost to it, right? Because it has to go through a function. Because this check is implemented still in my runtime library, written in Rust, so it's not inlined. But I figured even then, cost of a function call is not that big of a deal, right? Well, apparently in this case, it's 40% of the time. So if I turn it into a no-op, I think it went from like 6-7 seconds to like, I don't know, 3.5 or something. And then the other one's mostly because I don't apply optimizations. And if I tell LVM, enable the equivalent of 03, then it yanks it down to 1.5 seconds, which is about as fast as Python. So there's still a long way to go, but more reasonable. Now I had this issue created a long time ago to take another look at how the scheduler works. Specifically, I kind of want to get rid of this fuel mechanism because having this, decrement if now 0 yield at every single function call is expensive, even if you inline it, and even if you only do it in like specific spots. So say at the end of the loop or every 10 loop iterations or things like that. You're basically injecting a saturating subtraction, a check, and a saturating subtraction, and a conditional jump, and a whole bunch of places. So the idea I had at the time was to have kind of similar to, I believe, what Golang does. I believe what earlier versions of the Linux kernel did, where you essentially assign a time slice to a task, say, 10 milliseconds. And then you need a mechanism to preferably asynchronously check that. Say, hey, has this thing exceeded its time slice?
Yeah.
And then you somehow have to signal it like, hey, yield yourself.
There's a cheap way that Hotspot does exactly this thing for the exact same reason.
So I've been reading a lot of that. It seems that Golang nowadays uses, assuming this has been merged because it's from a couple of years ago, these documents, they appear to be using thread signals where they trap a signal against SIG-UGR, like some signal nobody ever uses, basically. And then they send that to the thread to have it interrupt, basically. But I'm so kind of curious what the sort of the general thoughts are. The challenge there with signals is that, at least in my case, as far as I know, there's no sort of cross-platform way to send signals. So you have to say, oh, on Unix, we have to do it this way, and on Windows, it's that way. And God knows how slow it gets on other platforms. So I'm kind of curious what the sort of general idea there is.
In the land of Azul's thread management situations where we wanted to make somebody yield after 10 milliseconds, we set a bit in the safe point handler he was going to check anyhow. So the safe point handler is not a read modify write because that will get expensive. It's just a read and a chest for null. So it's a load of thread local storage and jump not null to the handler, which is time to go yield. The thread local storage is because of 2 megabyte aligned stacks. It's a mask of your stack pointer. So copy your stack pointer, mask, load the 0 offset, jump if not 0. So it's a L1 cache hitting load to a particular branch. That's the running threads cost, and then you make that less expensive by having those safe point checks only periodically. In particular, every function call that you make has safe point checks internally, so we don't have one per function call. It's not necessary. Inside the function call, there had to be one before it came out. So before any function returns, if he hasn't safe pointed already, he has to do a safe point check somewhere in there. Fine. Then if somebody else wants to tell them it's time, when the timer interrupt goes off, whoever's saying it's time for you to be done, they just set the bit in this other thread's thread local storage.
Right. So I was thinking of a similar thing where essentially each task would have a atomic flag, which the specific idea is there is a sort of rescheduler thread, if you will, in the background, and that wakes up, let's say, every 10 milliseconds. And it has a atomic counter, which starts at 1, and it just increments it, wrapping around, skips 0. So what happens is every 10 milliseconds, it would wake up, it would sort of scan over all the currently running tasks and say, hey, what is your value of that counter? Those tasks would basically read that counter as they start. And it's then say, hey, if that counter difference is greater than, let's say, 1, that means it has been stored more than 10 milliseconds ago, or roughly. And then it would say, set that flag to 0 of the task, And then the task at certain points in the code has to atomically read that flag and say, hey, if that flag is now 0, we have to bail out.
So,
if it's anything else, we just keep going.
So what you badly want is the fast, efficient running thread to never write.
Right.
So he has to only read, and he doesn't need an atomic.
So that's where I wasn't sure. So it doesn't need to read indeed. Like in this proposal, the running threads only need to read this thread-specific atomic integer, right?
Yeah. But they don't need an atomic to read it. That's
well, and the ordering there will be relaxed. So it's atomic in the sense that at the CPU level, there's no memory reordering necessary. Because if it temporarily reads a value that's like slightly out of date, it's like, then it runs a bit longer, who cares?
Right.
The thing where you don't want is if you write some big counter that it like, how do you call it? Like it tears it.
If you have only on older systems, if you got or misaligned operations, you'd get tearing.
Right. So that's the thing. On x86, if I remember correctly, everything that is the size of the register is essentially atomic.
Yeah.
And it says if I write a 64 bits into 64 bits register, I cannot somehow read a 32-bit partial value from it.
As long as you're not misaligned.
Right.
Yeah.
The thing is there on ARM, that is not the case. ARM, as far as I understand, you need proper, like you need actual atomic instructions. Like if you have different threads performing regular reads.
Surely there is a minimum unit of atomicity that is the width of the buses. And that'll be 32
from what
unless you're on some tiny embedded thing.
Right. Put it this way, from what I remember, basically the ARM memory model is much less it's much more loose compared to
the Zulus
x86.
was much looser than x86 too.
We've got Arthur on here. He should be able to tell us how ARM works, right?
Right, but so if the concern with this idea is I was a bit worried that having this atomic check, even if it's just a read and even if it's relaxed ordering, might add quite a bit of cost to it.
To be atomic, don't be atomic. Be aligned. Figure out what your minimum alignment is for the hardware you're on. That's as many bits as you get to have in there. That's probably 32. It's probably 64 unless you try hard, but on some older, smaller ARM, maybe it's 32. And that's the set of bits you're going to read in one shot. Check it for equal or unequal to null and jump in a highly predictable branch. Make sure your branch prediction runs the right way. Don't put any atomic ops on the thing. Just load a word, jump not equal or equal according.
Yeah, he wants it to be volatile, right?
You have to be careful here. You have to use not the Java volatile, but like the C volatile.
Yeah, that's what I meant. Yeah.
Okay.
You read from memory, not from cache.
You have to read it from memory, not from a register. Yeah.
Oh, so that's worth adding there because from the reading side of things, it's okay if it's eventually consistent, basically.
Yeah,
right?
Exactly.
If I perform my check and it's still the previous value, I'm fine with that. So if the first time you read it, it's from cache and then the second time it's not, I don't give a shit.
Okay, cache is fine. You want to not let the compiler hoist it into a register and never reload it.
So hang on, Cliff. I'm going to say cache is fine as long as it's not already invalidated. So depending on the CPU, some CPUs allow you to read invalidated caches as an optimization. Some of them only allow you to read non-invalidated caches, and others have an instruction specifically for reading straight from memory. So
none of the CPUs that I ported hotspot to, which was a lot of them, ever had a situation where I could read a word out of memory, which would be cached, of course, and you want it to be cached, that wouldn't eventually become consistent when somebody else wrote to it. Missing one, as he says, missing one or two is fine.
Yeah, so we used to have a saying that, you want to design your algorithm so even when you're wrong, you're right, which is kind of what Yorick is saying. He's saying I can use the wrong value and still be right.
Yes. in the land of hotspot, we got safe point checks about every 1,000 clock cycles. So the most your 10 millisecond would be.
If you are fine with small round values, how about the costs of using relaxed atomics on ARM? Would this be still acceptable?
That's what I would do. Like when I think I mentioned when I was in this model where the threads that check the counter to see if they have to yield, they will always perform relaxed readings. Yeah. So no acquire, release, whatever, just relaxed. That's it.
Right.
The writing side, I think, can also just be relaxed because again, it can be eventually consistent. That's totally fine. And from what I understand, at least on the M1 chips from Apple, relaxed atomics are more or less the same cost as just regular reads. But I'm not entirely sure. But point being, I think if I go down this path, I'll probably just start with atomic reads because I prefer to be correct and maybe a little slower. And then at some point, somebody will come in and be like, actually, we can optimize this.
But they'll be a lot slower, or they could be a lot slower.
Right. I think for me, it was more like, does this general idea make sense? Or is it like, oh, God, no, you need to do it differently?
No. That all makes sense.
Right.
I just didn't increment the counters. I just had a bit that said it's time for you to yield.
I even recall that the use case for relaxed atomics is generally statistical counters. So something when you don't care about being off by a couple of increments.
I have a different issue with relaxed counters on statistical stuff. And that under heavy contention, you drop so many statistics that the numbers you get are essentially random. And I saw this repeatedly in ports of hotspot to different targets. You cannot have a high use, high density counter that's not atomic. It'll just be garbage numbers.
I have a completely different design if you guys want to hear more about thread scheduling.
Fire away.
I will just one thing, Yorick, there is a quote by Travis Downs on concurrency costs, and it evaluates costs of different operations on both x86 as well as ARM in Graviton CPUs, including atomic adds. And some of the atomic adds don't look so bad. There's multiple things you can do. You can do also a CAS add, which is beginning to look bad, but get spin, get blocking. So I would look at that blog post and see if there is something that may be reasonable.
Yeah, thanks. Now that I see it, I think I've actually seen this post before. But yeah, I'll take another look at it.
And certainly in hotspot, I didn't do anything on the reader side except read, but the writer did a CAS because he set different bits according to what job he wanted done. So they CASed on the right side.
So I guess one follow-up there for hotspot. I guess the situation is a bit different because it already has predefined save points needed for garbage collection. I'm kind of curious with the sort of interrupt handling, the yielding. Did it insert these sort of extra checks in additional places? Or no. So my line of thinking was basically, you need to insert these checks somewhere. Doing it after every call is kind of overkill. So you could do it after, let's say, the end of a loop, but then you have to account for infinite loops around I/O and maybe calling to C through an FFI.
We have a very well specified technique or technology or whatever you want to do it here. The rule was you couldn't go more than roughly 1,000 clock cycles. So you had to look at what the processor was doing. And out of that came the save point information had to be described at every call site. Anyhow, so you could stack crawl. This is for incremental GC. So we had to take these save points periodically for the incremental GC anyhow. So it meant that all call sites already had a save point check internally. So you couldn't have a call take a shortcut in and out without also save point checking. And then on all flow paths through the code, you had to have a network slice cut that had a save point check. That had to be all paths had it. This was actually done by having the parser throw in save point checks at every return and every back edge. And then after inlining, the optimizer would clean out the extras. And if he loop unrolled and he'd screw around with loops, whatever, loops always had them. And then he would get rid of extras along all paths until you had basically just one, unless the path was super long. And then he might stop and leave 2 or 3 or something. But you rarely had one on any one path through a function, even after inlining. Loops always had one to start with. Then I went to a place where counted loops, which had a therefore known finite but could be large trip count, would not have them. That helped a lot for everybody doing anything with big array math. Every blaz, like, I'm going to walk 1 billion elements. If you walked 1,000 elements, you didn't care. It was usually really quick. There's no function calls here because those already had a safe point. So I had a loop with no function calls, a trip count under 1,000, you were almost always fine. You had big trip count and a regular loop with no function calls in it. That turned into long GC pause times, waiting for that loop to get to a safe point. So then we went to unroll and jam. But they went through them steps. Like, to start with, I would say throw in the back edge, throw in on the return, inline and optimize, get rid of extras on any path.
There's also this paper called Compiler-Based Timing for Extremely Fine-Grained Preemptive Parallelism. And what it does is basically it's static analysis with a cost model to estimate the cost of the instructions in your intermediate representations. And if you want to have some bound that I want to switch every n couple of time units, then you can insert those yield points based on that estimation of the cost model. So you can play some tricks there.
The hotspot basically said it all costs 1. And if we counted several thousands in a row, then we'd leave the safe point in. But yeah.
When you mentioned back edge, do you mean like the end of the loop, or the end of the iteration, or like?
No, a classic control flow graph and a classic C compiler produces a classically shaped loop, which has a fall into the top and a back edge that loops back around. Okay, somewhere down here, the back edge has to be just a reverse jump. So your efficiency on the processor, there is just a reverse jump. So the fall in code somewhere near the bottom, anywhere, not in the bottom, anywhere.
Right, okay, yeah, so it's basically
path.
At the end of the iteration, I suppose.
In the dominating path, it didn't matter if you were before or after, because I took this loop and then I would peel an iteration. Well, he had a safe point in the peel. So you had a safe point just prior to the start of the loop head. Kind of didn't matter. I couldn't move the safe points around conveniently because they carried the Java semantic mapping. So to move a safe point, I had to take the Java semantics and move it ahead or behind to the safe point. But by the time I got to that, I didn't have any bytecodes to semantically look at. So safe points got nailed down semantically in the parser. And then I could get rid of them and I could clone them, but I couldn't slide them. So I mostly just got rid of the extras. But yeah, every loop had to have one on a dominating path through the loop.
In that paper, they insert the checks at the entry, the exit, and the latch. And the latch is the basic block that jumps to the continuation of the iteration after the loop condition check.
Yeah, I put them in the bytecodes because I'm mapping 2 bytecodes. I couldn't insert them after the fact. Like the optimizer could never insert one. He could clone an existing one. He could delete. He could not insert. You had to have.
Should I go ahead or?
Oh, sure.
Yeah. Oh, yeah. Levo, you were stalled a long time. Sorry, Onad. Levo was waiting a long time.
No, please, of course.
So the way I was thinking about handling my thread scheduling, I didn't write any code whatsoever, and I was thinking maybe I don't want to do safe points because I have no idea how to do them, and I have no idea how much work they're going to take. But and my code already generates the C, so I was thinking, what's the easiest way to do this? And I was thinking every time I schedule a thread, this would be a green thread, not a hardware. I would grab the current time.
Question: are you going to have a runtime like JVM?
I implemented my own replacements for instead of depending on C runtime, I wrote my own runtime, but it's not going to be.
It's not a virtual machine. Then if it is not a virtual machine, it's unlikely that you are implementing green threads. Green threads are generally what is terminology for user space threads that run under the control of a runtime. Usually runtime as is Java virtual machine runtime. There was a very old Java implementation, maybe Cameron or Cliff will remember, with Java 1.1 or something like that, when it had green threads. And what was called green thread is that you can have multiple threads that are running on one and only one hardware thread. So this is what green threads meant historically. It did not work out very well.
It was necessary for both the 68,000 and the Windows 3.1 because neither of them were multi-threaded.
That's what I mean by green threads. It's just one hardware thread.
So yeah, if you don't want to use multiple cores on a computer, you definitely want to implement the old Sun-style green threads, which is
yeah. My thinking was I need this for servers, like HTTP requests.
Yeah.
So
and usually you use multiple threads. I think you just want user mode threads, but you don't necessarily want to restrict yourself to green threads.
What's okay?
So user mode threads is when you have M to M. So you have maybe 1,000 logical threads in your program, but maybe you have 4 physical cores. Green threads, if you only have one and only one and forever one physical core and never anything else.
Well,
at least historically.
Not just one core, but also one
physical
thread.
Exactly.
If you only have one OS thread, then you have to implement green threads, or your language can't have threads.
Okay, so user mode thread, or
user mode thread. Yeah, user mode or user space interchangeably.
You still usually have some kind of a runtime to manage the user mode threads, but
so implementing the runtime is where I'm a little foggy about.
Or an execution pool. You may actually look into the executor proposal for C++ because that's some of the problems it has to solve. Because different users may want to have different scheduling policies, and if you just put one in the runtime, then you have to make your runtime configurable, which may or may not be easy.
There's only one user.
It's probably best to start with OS threads, because no matter what, you're going to need support for those. Otherwise, no one will ever use what you build. So you need OS thread support first.
Yeah, so so far with threading, my compiler, I'm able to make multiple threads, like hardware threads. So that's done, but the user space threads.
No, back up. You said hardware threads? You can't make hardware threads.
I think he means OS threads.
Yes, so let's use the right word. So OS threads are what you want to support.
Yes, yeah. So
just for distinction, this is also called kernel mode threads if you want to have a contrasting term with user mode threads. But I would stick with OS. It's
Let's
easier
just say OS, yeah.
Yeah. Just explain to leave out this is the contrast, kernel mode versus user mode, and you have different trade-offs you can apply before.
Yeah, so user mode threads will drag in a lot of work and probably not a lot of benefit for quite a while. So I would avoid those for, say, the next 14 years.
Yeah, so this is why I'm in the design phase and I didn't implement it. I just did little bits here and there. But anyway,
I will write the OS thread scheduling for you. So you just write the thread support in Bolin, and I will provide preemptive OS thread scheduling for you on Win64, Linux, and Mac OS. I'll write it myself. I'll put it in the OS for you.
What's that offer? What's that offer?
So how do you keep a straight face, sir? Fine.
So I was just so the problem I was thinking about is so the idea was when I start a user space thread, I would grab the current time, like in nanoseconds.
Don't start a user space thread.
Let him I'm going to do that and put it into a thread local variable because I would want to have more than one OS thread. So I just stick the current time into that variable, and then I would just run the code, and the code could just be a spin loop that never exits. I also have Linux giving me a signal every few milliseconds. I think I had it set to 5, and I was able to grab the thread local time, compare it, see if it's more than 5 milliseconds, and then I could do something on that. But the thing is, I figured that this would be really cheap. There's no save points. There's no counters I have to touch. It's just every 5 milliseconds when I get the signal, I look at it. And every time I switch the user space thread, I update the time. So the issue with this is I have no idea how to tell the signal handler not to return to, like, how to change them where the instruction pointer is pointing. So yeah, I think I would have to
That
either
jump,
not
long
do
jump.
Yeah, but you have to, like, from what I remember, you have to return from the signal handler, or else it gets all weird. But that might be just a C implementation thing, and I just have to figure out how to do it with like system calls instead of C.
So I have a question. Who here in the CCC works with thread creation and raw thread manipulation for concurrency?
Thread creation.
Well, I did the OS
Thread
creation.
So I'm envisioning Java threads. You manipulate manually. So manually creating, manually starting, manually destroying. Who does something like this in 2023?
I mean,
I certainly create threads with create thread, and it's fun.
Okay. Not is one. Okay.
Oh.
Anyone?
Like, what exactly do you mean? Like, in terms of you have a language that does that, or as you write a program, you import a thread library and you do something like, for X and Y thread.spawn or something like that?
Yeah, create a thread and manage it manually. So it doesn't.
I mean,
over
the years did that quite a
basically,
bit.
threads versus tasks. I did use threads, but I also use tasks with actual task scheduler. Yes, can be useful. Most task schedulers are not very great, I have to say.
Yeah, a task scheduler.
Go ahead, Tony.
Is there like a system call to be able to suspend a running thread from another thread? I think so for Linux and for Windows too, right?
There is, yeah.
There's all kind of caveats they don't tell you about when using it, but it's there.
Oh yeah. I thought, like, I never used it. I thought I've seen something like it, but I've never used it. What are the caveats exactly?
For me, the biggest caveat is having suspended the thread, the OS cannot reliably tell you anything about its stack pointer and program counter. It can tell you with 99.9% accuracy what its stack pointer is, so you can crawl it for GC, but about 0.01% it'll lie, give you garbage, and your GC will then crash because your stack numbers are off. And I asked several times over, while this was an important part of my life, over decades, and I got the same answer from several different OS people over a 20-year span, which was, yeah, we know it's pretty good, but we know it's not perfect. Yeah, sometimes it can screw up.
Oh, God.
As a provider of a high robust system that takes constant context switches and has to preempt threads at save points and the like, I cannot rely on the OS call to give me this registers.
Right. Yeah.
But
that's unfortunate because, like, you.
Yeah. And resume works as long as you don't change anything.
Yeah. Right. Yeah. So instead, preemption on Azul boxes at least was all done software-wise. You took the save point check, it failed, and you promptly called yield at a well-known spot. The other part of that one is, of course, is if you're yielding and you're off the CPU and you're not running, then the incremental GC can crawl your stack while you're blocked. And other threads are running, so he only has to crawl at a pause point, only has to crawl however many cores worth of running threads you have. All previously stalled threads are all at save points, all got their stacks called in the background. So that was.
Is there like an easy C program someone can write to test if the OS, or just find the OS giving bad numbers, like reproduce that bad number?
So I saw this relatively rarely at Sun, even when we had millions of Java users. It definitely was happening. There's still code in Hotspot to filter out bad SPs, and under very low frequencies, you can get fooled by it and crash. But the kind of things that cause it or to demonstrate it, I never got a clean handle. The theory was that you took a page fault and a Stack Overflow handler in a, disk swap space out of memory handler, and somewhere in there, your thread got paused and stopped, and some other thread got a chance to run and asked the OS and got a garbage number because you were nested inside a kernel handler for TLB slash, page fault slash disk sector fault read, blah, blah, blah. So I don't
it's
know
really
that,
rare then.
but it wasn't, it was rare. Oh no, it was rare. I said 0.1%, but it's probably closer to 1 in a million, 1 in a billion.
But the
So
problem
if
the problem is with a 1 in 100 trillion, you hit it all the time. Somewhere in the earth, someone's
Right.
hitting it because you just got too many people running too much code.
So would it be like an exception in the exception handler itself, or like when
You got a poison stack pointer and you crawl to stack trying for garbage collection. If it crashed early, all you know is your heap is fucked, your stack is fucked, your process is fucked. It's time to bring it down. But the general problem is that you would fail to do a valid garbage collection, and 10 or 20 garbage collection cycles later, somebody would reach for a pointer that had been reclaimed, was now overwritten with something else, and you get garbage data out, and your bizarre crashes would happen.
Wasn't the fix though to simply set a flag and then let it continue to the next set point or something? So
if you could detect that the SP was borked, like I said, there's code in Hotspot right now. He looks, if he thinks the SP is borked, he simply, sets the flag and goes again and takes the next interrupt a second later and see if he can get a better one. You can get fooled by that check, though. That check says it's in bounds, it's on the right stack frame, it's this, it looks good, but it would be incorrect with low frequency, and I went to a different technique, the safe pointing technique, to fix that.
Nice. I could demo, sorry, I could demo 6seg handling like in my new language if you want, real quickly.
Well,
it's only 15 minutes left.
A few minutes, we'll do it, and then but I think we're going to wrap up before long. But,
sure, I mean, that's...
fire away.
Oh, okay. So I'm going to try to share the screen. If it works, okay, works, yes.
You could fix the retro screen warp, but fine.
Oh, is it like messing the compression, or?
No.
I like it.
It just, I get it. It doesn't help your audience read your stuff. So.
Yeah, sorry about that. So the crash handler is here, and the recovery assembly looks like this. Actually, oh, there it is. So
it's forth. You got to give it a second to go read. Oop, all right, and you flip screen. So
sorry, I have to move this over to the right so that we can see the full assembly.
Okay.
So let me start that. Okay, now we can see the full assembly. So yeah, it just looks like this. In Linux, you get like a pointer. I mean, you get jumped to a place. Let's see. Where RDX is holding all of your data that you're interested in, and it's just an array of 8 bytes. And I just figured out what the values were by reading the source and then experimenting here, and then over here I get a piece of code that says like, okay, let's start on the it's doing something that's like reading from the offset and then like writing back to the place where I've allocated here so that I can display the registers later. So in the new language, so if I say like, actually wait, I can open the oh, there it is. So if I have,
you still think faster than you explain.
Yes, your fingers are moving.
Sorry, what?
Faster than your fingers are moving faster than you're talking.
Oh,
and your thinking is moving faster than your fingers, so we get this asynchronous
disjoint. Yes, it's definitely disjoint.
Sorry about that. So I can actually show like how my language is. I've done something that something that's quite original and speeds it up like by 6x, but decreases the stack size considerably. So so I got like a different an older version.
We're changing topics from exception catching to jitting. I'm asking.
If you want to, I mean, I can show like something that's cool that I've just done. So if I look at the symbol disassembly for this symbol, the way I used to JIT this is like I store the stack pointer at RBX, like BL, that you can see up top, like over here. And then I move the racks, like I store the top of stack on racks, and then I move racks 1. So this is bad because it's doing all of these like stack operations, or if I load like a variable, it still has to do the stack operation, but the upside is you got potentially like an infinite stack, right? But I don't really need that much stack size. I just need like 2 elements. So I thought I would instead do this, where I'm storing only 2 variables on the stack.
You're getting 4th code, yes?
Yes.
Okay.
So that I can execute and interpret it faster, but also I can do stuff like, I want to return early, for example, in this function, and I can just inline whatever opcodes that I need to extend the language in ways that I need. So I can also write inline assembly like this. So and so I've just got 2 top of stack, like I've got a stack of size of 2, and I store them in racks and RDX. And at the beginning of each function, I get this instruction like exchange racks RDX. And that's because in this calling convention, for when I'm entering like a word, when I'm entering a word, I want the top of stack to be at racks. And when I'm exiting a word, I want the top of stack to be at racks too. So that's that. And like I can,
You've inlined a couple elements of the stack into registers, and you're doing the necessary register shuffles internally.
Exactly. And
this is not new, by the way, but it's definitely helpful.
Really, it's not new.
It's similar to code I've seen generated. So the entry point of the first thing.
I was doing this kind of thing when I was 15. So bad news for you. I wrote my first compiler when I was 15.
But he wasn't using racks.
But were you doing like exactly this kind of like store 2 registers and then have like a stack of like 2? Kind of?
I was doing 1 register, and I knew I could have done 2, but the jump from 0 to 1 was huge. And the jump from 1 to 2 was a lot less huge. And I was bored, so I pivoted and wrote a breakout game in my language.
So wait. You got 1 register. How do you program in a Fort style with 1 register? Like
I got a stack. I got Z80. I got a stack, like every other processor of that era. Well, all of them still. It has a bunch of registers, but 4th is all stack to stack to stack. And I cached the top of stack in a register, just like you did, just 1 register. But I had an official stack. It never, 4th program doing breakout didn't get super deep, but it had more than 2, because however I needed to do graphics calls and track a moving ball and move your mouse, or not mouse, keyboard for your paddle and all that.
I mean, to be clear, I'm eliminating the stack here entirely to just 2 registers, and like the entire stack space I don't use. Like
if I was able to fit such a program in 2 words of stack, then it would have also done the same thing. But I lived with 1 and had more words on stack because I'm doing a bunch of graphics.
And
I see your calls to neg and imul and idiv and all that down below. You're making calls, so you're burning stack there.
Well, that's sort of like stack as in return stack, or like working stack, or data stack as we call it. So
the data stack, right? You're right. I had 2 stacks. It's standard Fort, 2 stacks. You got a control stack, a return stack, and you got a data stack. And my data stack had more than 2 elements because I was doing stuff that needed more than 2 elements.
I realize I don't really need to do stuff with more than 2 elements, because I think of it as I'm not really running this at the runtime. I'm running this only at compile time. But I would still like to, instead of suffer the interpreter loop, I would rather inline it. And inlining like this makes it a lot faster than the interpreter loop. but then you still have the stack hops. So with this, I mean, it should fly. I haven't done the performance numbers yet, but like this is free. Exchange Wax RDX in a modern processor is free. Move from a register free. Like all of this, most of this stuff, like move a register, like it's literally free. Like the only stuff.
It's free up till you get 10 or 20 in a row, and then it costs you, but it's mostly free. Yes.
It's translated. It's translated in the CPU before it even gets to execution.
Right. Exactly, the internal register renaming stuff that happens. And,
all right, sir.
Yeah.
Like I said, though, the go to fit in 2 stack words so you can do it in registers, I didn't do, but I didn't fit in 2 stack words. I definitely inlined my assembly code to get out. I had an interpreter loop. I turned it into an inlined assembly loop. I unrolled the interpreter and inlined as I went. And then I did cross 4th word optimizations where I looked adjacent stack words and folded them back into registers. So pushes and pops across word boundaries would fold up. That was, so this is, and that was not new when at the time I did it. So this stuff's been around since 60s, 70s. I was certainly doing it in the 70s.
And you were spoiled both having 16-bit registers and more than 2 of them.
Yes.
The thing is, most forts I've seen are incredibly complex. Like they're using links between words and so on.
In 6502, you had 8-bit registers, but the program counter had to be in 16.
Yes.
Yep. Yeah, you had 2 8-bit registers, X and Y, and that was pretty much it.
Yes. Yes, I got on a Z80. It was
hot. Should be enough for everyone.
All right, I think we're done with this for the moment.
One last thing that I just did was like the stack visualization, of course, over here. Like I got like whenever I press enter, I can see like the stack.
Onet, save your one last thing to the next go round.
But I've done it already this week. Like I'll have much more stuff for next week. So
that's all right.
Anyway,
but thank you.
Thanks.
All right, folks.
Yeah, thank you.
It's all good. See each other next week.
See ya.
Bye-bye.
Yeah, see ya. Bye.